Hi, good afternoon, everybody. So in this session, we have three talks. The first is by Subhasis Sinha, second by Sebastian Wooster, and the third by Manas Mukherjee. Our first speaker is Subhasis Sinha. Subhasis Sinha is from IISER, Kolkata. So he did his PhD from Institute of Math Science, and after that he has held various positions at various places of renown. And his interest is on ultracold atoms with a perspective from condensed matter physics. And in recent times, he has been working on these quantum scares. And today he will be talking to us on chaos and quantum scares in Bose-Josephson Junction, coupled to a bosonic mode, a topic that's of great interest considering the use of these finite-sized quantum systems in quantum information. So Subhas, is over to you.
Okay, thanks Dilip for this nice introduction, and I also thank the organizers for giving me the opportunity to present this work. So today I'm mainly talking about the quantum scarring and chaos in Bose-Josephson Junction coupled to a bosonic mode. So the outline is the following. So first, I'll just briefly discuss about the ergodicity in the quantum system, closed quantum system, and next I'll just go to the Bose-Josephson junction coupled to the bosonic mode to discuss the chaos and ergodic behavior and scarring phenomena. And all the meaning, since this conference is basically on the cold atom, so that's why I choose this topic, that's a Bose-Josephson junction. But the scarring phenomena can be seen in the other systems also, but there's another system which is also interesting in the context of cold atom, which is a kick top. So I just briefly discuss, although this is not the main focus of the present talk, but still if time permits, I'll just discuss about the scarring in kick-top model, and then I'll summarize it. So this non-equilibrium dynamics and ergodic behavior of isolated quantum many-body system has become an interesting topic in recent years, particularly because of lots of ongoing experiments on cold atom, because cold atom system, particularly in the optical lattice or the strongly correlated systems in the optical lattice, has become a test bed for studying such non-equilibrium phenomena. And also this ergodicity is basically a pillar for statistical mechanics, which we generally study in the undergraduate level, but its root or how it's originate in the quantum mechanics is not very clear, because in classical system it is quite clear that there is a this ergodicity arises from the phase space mixing of the this chaotic trajectories, which is basically triggered by some chaos, etc. And but such type of mechanism is absent in an isolated quantum system, since there is no such description of phase space or phase space trajectories because of the uncertainty principle. And so that to explain the thermalization in an isolated quantum system, there's an eigenstate thermalization hypothesis has been put forward, which proposes some type of thermalization for each eigenstates. But and it has a close resemblance with the random matrix theory. Also, the if the quantum system shows a signature of chaos in the quantum system, can also understood from the random matrix theory. So in this context, the random matrix theory plays a very important role to understanding the ergodic behavior of the quantum system. However, it is not very clear that which quantum system will thermalize and which will be the degree of ergodicity of different quantum system will be quite different. Mm. So there are different factors which hinders the thermalization, and also the violation leads to the violation of eigenstate thermalization hypothesis. So one is of course the integrable systems, because there are lots of conserved quantities, and that hinders that is generic belief is of course that this will not thermalize the integrable system, rather non-integrable models are better for thermalization. But there's a very interesting example which is found in the recent year, which has become very popular in recent years, that is the many body localized system, where not only the ground state, even the excited state of the systems remains localized, and it is hindering the thermalization of the system. So there are also certain systems has shown the non-ergodic phases, where the system has some sort of states which are in between, which is intermediate between the localized states and the plane wave like extended states. So they are neither completely localized nor completely extended. They are called the multifractal states. So presence of the multifractal states make the quantum system very interesting. They show some sort of anomalous thermalization, etc. And recently it has been also found out that there are certain specific type of initial states that also shows in the non-equilibrium quantum dynamics a athermal behavior, so which never relax to the thermal states. So these are attributed to many body quantum scars. So I'll mainly focus on this phenomena of quantum many body scar in this talk. Okay. So, like one example of this localized phase of this quantum system can be achieved by this quasi-periodic lattice. So, quasi-periodic lattice is created by these types of potential, where beta, this parameter beta, is considered to be a irrational term, typically some sort of Diophantine number or golden ratio, etc. And this model, in case of a nearest neighbor hopping term, this model is known as the Andrew-Abreu model, and it shows a localization transition. And even with different many body localized states, even the localization of light, etc., has been realized in this creating this quasi-periodic lattice. So this is very common in the present in recent years. So we have studied this thing with a long range interaction, not long range hopping term, not a just a nearest neighbor hopping, but long range hopping. And this gives rise to the non-ergodic phases, not only localized, but the non-ergodic phases, depending on the power of this hopping term. So if A is less than 1, then one can say these types of non-ergodic phases also. Also, there is a possibility to see a simple system, very simple system, like a driven spin, but driven in the quasi-periodic manner, so that there is some sort of sequence like the Fibonacci sequence. The spin is driven by the or kicked by the Fibonacci sequence. In that system, it shows that the phase space trajectories shows quite a chaotic behavior, irregular behavior, but the Lupinov exponent vanishes. So this is a very strange system, and a closer analysis also reveals that there's some sort of fractal behavior of this dynamics of the spin, and also the evolution operator. If one study the eigenvalue, the eigen properties of the eigenvectors, it shows the multifractal nature. And in presence of interaction, this also undergoes from the non-ergodic phases to the ergodic transitions. It's possible. And in a recent experiment, this many body quantum scarring phenomena has been observed, where there's in a chain of Rydberg atom, experiment is done on a chain of Rydberg atom. And if one starts with some special initial states like a charge density wave-like state, so this is the initial state. It turns out that these types of particular, some special initial states do not relax or do not thermalize. It ultimately shows some sort of a revival phenomena like this, some oscillatory or revival phenomena, and it does not thermalize, unlike other states which are very in this strongly interacting system. Many other states also thermalize, but except a few. And this is clearly the violating the ergodic evolution. So typically in the ergodic evolution, we expect that it should be a Markovian nature will be there, so the memory will be lost ultimately. But there is a memory effect will be still retained in such thing, and that's why there's a revival phenomena is there in this scarring phenomena in many body system. But originally the quantum scar was proposed for a non-interacting chaotic system, and like the chaotic billiards, where the analyzing the eigenstate shows that there's a reminiscence of the unstable periodic orbits. So orbits are unstable, they're not really existent, but still their reminiscence can be found in the wave function. So that was termed as the quantum scars. So what is the connection between the underlying unstable dynamics and this many body quantum scar, which just violating this ergodic behavior or violating the ETH hypothesis, etc. So what the connection is not very clear, that what is the underlying unstable dynamics behind such formation of the many body scar. But if one start to answer this question, I think it is better to study some sort of collective models which shows the underlying connection. So in that context, I will consider a model which is already studied in the cold atom system, which is the Bose-Josephson Junction. So this experiment has done long back, and this Josephson junction is created by loading the condensate in the double well trap, and this is the some effective Hamiltonian describing this model within the single mode approximation. So first term represents the tunneling between the tunneling of particle between these two well in the left and right well, and the second term is the interaction, the on-site interaction of this. So this is like the Bose-Hubbard dimer, a simple model. And this model has been analyzed semi-classically, and the different type of dynamical branches of this oscillation has been studied in this work. There is a nice theoretical work, and also lots of experimental work has been done where there's a very interesting phases are observed. So there are three different types of oscillatory modes can be observed in the Josephson junction. So first of all, there are two collective variable in this case. One is the number imbalance, the number difference between left and right well, and the relative phase between them. So this model can also be described in terms of a large spin system. So I'm not considering this thing, but effectively in terms of these collective variables z and phi, the classical Hamiltonian can be written in this form. Okay. And analyzing the equation of motion of this classical Hamiltonian, one can find out the steady states and the oscillations around such steady states. So first type of oscillation is the typical AC Josephson oscillation, which occurs around the zero number imbalance and when the phase difference is zero. So that the frequency of this oscillation is this, and it is always stable for all parameters. There is another interesting branch of oscillation can be seen, which is called the pi mode or pi oscillation, where the imbalance is still zero, but the relative phase is pi in that case. And the oscillation frequency looks like that. And so it is very clear that this becomes unstable. This pi oscillation become unstable when coupling constant exceeds this value j. And there is another self-trapped regime, which occurs in the strong interacting regime when u is very larger compared to this j, and there is a spontaneous imbalance will be formed in this system. So in this picture, this is a theory and experimental work, and there are these two types of oscillation. The AC Josephson junction, that Josephson oscillation is shown by these blue lines, and this red colored thing are the pi oscillation, pi modes. This can be seen. So our in this work, I'll mainly focus on this pi oscillation. So this is the main focus of this present work. So this is just a simple isolated Bose-Josephson junction, and there these types of mode, this pi oscillation can exist and which can become unstable in some parameter regime. Now, second question one can ask that it's interesting to see that study these types of dynamics in presence of the dissipative environment. So the dissipative environment can be generated by this coupling this Bose-Josephson junction with some type of phononic bath, which can be created by coupling it to some two condensates in the left and right, so that the Bogoliubov modes can couple to this left and right side of this Josephson junction, and this will act like a bunch of oscillators coupled to the Josephson junction, like a caldera Leggett model, which gives rise to the dissipative effect in the Josephson. We studied the fate of the different types of pi mode and the imbalance state, this self-trapped state, etc., in presence of dissipation in this work. But this is the in this case, of course, when you consider a bath or a dissipative dynamics, there that differ many modes are important. So there are many k modes, like the Bogoliubov modes are present in this case, they are coupled. But we are considering a simple case when there is only one bosonic mode is coupled to the Josephson effect, and what happens to the system. So this can be achieved maybe coupling the Josephson junction with some cavity mode, and we can, this is described by this Hamiltonian like this, and this can be written in terms of spin Hamiltonian with a very large magnitude, where S is n by 2, n is the number of particle. And in the spin language, this Hamiltonian can be written in this form. So Sx term gives this tunneling between left and right well of the Josephson junction. Sz square gives this interaction term. And then there is a Sz with a B plus B dagger that gives the coupling with the bosonic mode and the Josephson junction. And omega 0 gives the mode frequency of this. So the effective.
Hi,
Ah,
Subhasis. There is a question in the chat box.
oh,
So the question is, can you please tell once again what is quantum scar?
okay. So, well, so this is the original work of Eric Heller, where the quantum scar has been proposed. So in the chaotic system, studying the chaotic system, the wave function of the chaotic systems shows that reveals the some reminiscence of the unstable trajectories. So here, if you consider, it's a non-interacting system, just but because of the geometry, the system shows chaos. So classically, if you consider the different trajectories, this becomes chaotic because of this bouncing, and these trajectories become chaotic and completely filled up. So the reminiscence of these unstable trajectories is called the scar, typical, the quantum scar. But the many body quantum scar, which has been observed in the recent experiment, these are like some initial very complicated many body states, which gives rise to athermal behavior, particularly the revival phenomena, and violating the sort of ergodic behavior or the ergodic dynamics. That is the many body quantum scar, which is called in the present experimental context. Okay, is it clear, or any question?
Yeah, it's
If
fine.
there,
Yeah, you
okay,
can
if there
continue.
is any question, please unmute your speaker and please talk to me. Okay. And okay, so yeah, so this is the Hamiltonian. We are considering the Bose-Josephson junction coupled to a one bosonic mode, and the semi-classical description of this system can be written in terms of the coherent states, which are the one is the spin coherent state, another is the bosonic sector. We can consider the bosonic coherent state, and within that prescription, one can obtain the classical version of this Hamiltonian, and where P and Q are basically the bosonic mode, can be written as a classical harmonic oscillator with coordinate P and coordinate Q and momentum P, and the equation of motion, etc. This can be analyzed. So this work is actually done with my student Sudeep Sinha. So, and the interesting thing is that this model, although the isolated Bose-Josephson junction does not show any type of quantum transition, but when it is coupled to the external bosonic mode, it is somewhat similar to the Dickey model. And it shows a Dickey-like transition, a quantum transition in this model. So there is some critical coupling strength, gamma C, above which the system will show a spontaneous imbalance will be generated in this system, and that's a quantum phase transition, which can be detected by calculating the different quantities, physical quantities like Sz, etc., spin component, or even the entanglement entropy of the ground state that shows a peak at this transition point, etc. uh, and the energetics in that, the energy level, the etc., can be shown in this figure. So this figure actually shows the variation of the ground state with the coupling with the bosonic mode. So where there is a kink like structure is there, that is the point where the quantum phase transition occurs, and then the ground state actually shows a symmetry broken structure, etc. And here the color scale plot shows the ergodic properties of the eigenstate from the entanglement entropy. So we calculate the degree of ergodicity of eigenstates from a relative entanglement entropy. Calculate the entanglement entropy by just integrating out the bosonic modes, and then find out the maximum entanglement entropy in that case, that is for spin system of large spin, which is log 2s plus 1. So we find out the relative entanglement entropy behavior. That is very clear that near the ground state, the states are not very ergodic. Degree of ergodicity is less, but as you go to the higher energy states, this will become ergodic. And above the quantum phase transition, there are three steady states can be there. One is the symmetry broken steady state, which is basically the ground state drawn by this red color thing. That's the thing that is symmetry broken steady state. Then there is a symmetry unbroken and unstable steady state. So a phase transition can be viewed as just a bifurcation, simple pitchfork bifurcation type, and so that symmetry unbroken branch will be always unstable after the phase transition, and that's denoted by this dotted line at energy density EC. And moreover, there is another steady state is present which corresponds to the pi oscillation of this mode of the Josephson junction. That's is denoted by this E0. So you see that the pi oscillation, pi mode can still exist above the quantum phase transition and well inside the state regime where the states are quite ergodic, quite large entanglement entropy. Okay. And we will see that effect of this pi oscillation in in this regime. That is the main objective of this
Hello.
work. It also, hello, yes.
Sir, why the energy, and is it negative energy? Minus 1 EC.
Yeah, it is indeed negative energy density. In fact, this is not the energy divided by s, the magnitude of the spin is called. So yeah, it can be negative, yeah. Okay, there is also another interesting transition that occurs in this system, which is called the excited state quantum phase transition. This occurs at this energy density EC corresponding to the symmetry unbroken state. Basically, it separates the states in the two parts. So the below this line, this EC, the states have some sort of symmetry broken nature, and the above this line, the state shows some symmetry unbroken nature of this. So anyway, this is not very important in this context of scarring, but this is an interesting phenomenon. And also we study the classical dynamics of this. We we just analyze the fixed point structures, etc., but we can do the full dynamics of this system and calculate the phase space structure. It shows that after the quantum phase transition, there are this phase space shows a very chaotic, very irregular type of behavior, although there are this symmetry unbroken, meaning symmetry broken phases after quantum transition. These are quite visible. This they show regular regime, but this regular region in the phase portrait that shrinks, and there's a field with the irregular trajectory. So it's just classically it indicates the chaotic behavior. Also from the entanglement entropy of the energy eigenstate, we have seen that there's a very states become ergodic as you go away from the, above the quantum transition, and higher energy states becomes more ergodic in that sense. So we study the level spacing, the spectral statistics of this system. It shows that above the quantum, meaning below the quantum transition, it shows a regular behavior, and regular behavior meaning is a level spacing distribution, is a Poisson statistics. It is according to the Barry-Tabor's theorem, or conjecture rather, that regular system, regular behavior is demonstrated by the Poissonian statistics. And BGS conjecture says that the Wigner-Dyson statistics can be observed in the chaotic regime. So where we can see the classical chaotic behavior, if we analyze the spectral statistics, it will reveal these types of Wigner-Dyson type behavior. That's also we observed. And there's another parameter, it's called the ratio of level spacing ratio of levels, consecutive level spacing. And if we calculate the average value of this quantity, this also shows a transition from Poisson to GOE around this quantum transition. So in this regime, the system becomes chaotic. It is expected. So it's become more ergodic and chaotic. But as we have seen from this figure, that although the system is showing ergodic behavior, but there is still this pi oscillation state still persist in this regime, in the ergodic regime. So what is the effect of this pi state here? So if we calculate the frequency of the pi oscillation, it shows this behavior. This is the frequency analytically one can find out, and it turns out that this becomes unstable above this critical coupling strength gamma u is given by that, and this instability value that can be tuned by tuning the frequency of this mode omega 0, that very much. So if I fix the gamma value and just tune this frequency of the mode, we can get the regime where the pi mode is stable or it can become unstable. So if we consider the regime when this pi mode is unstable, then we see the phase space, or the Poincare map is called. So that shows at this energy, the energy of this pi mode, it shows a very chaotic behavior. Whereas when this pi mode is stable, then it shows a mixed phase space like behavior when there is a stable region around the pi oscillation. Also, the entanglement entropy shows when this pi mode is stable, then it shows a dip in the entanglement entropy around this energy density 1, where this pi mode occurs. And if the pi mode becomes unstable, then of course the entanglement entropy just increases without such dip. So we also calculated this level spacing ratio, average of the level spacing ratio. It shows the very clear effect of this stable pi mode, the presence of stable pi mode. It reduces the chaotic degree, and when the pi mode becomes unstable, then it increases the chaoticity, or R average, that shows these things. Also, the entanglement entropy shows the dip in the entanglement entropy, shows the opposite behavior, of course. So there is a clear effect of the underlying dynamical steady states on the ergodic behavior of a quantum system, it shows. Next question one can address: what happens when the pi mode become unstable? Can we see the signature of this unstable pi mode? The answer is yes, we can see some signature. So if we calculate the Shannon entropy instead of the entanglement entropy, if we calculate the Shannon entropy of these states when the pi mode become unstable in the chaotic regime, we see this behavior. So most of the states, the Shannon entropy forms a band-like structure. However, at this particular energy E is equal to 1, the pi mode forms. So around E is equal to 1, we just studied the structure of the Shannon entropy of the states. But there are certain states which shows a strong deviation. And we just picked up certain these states which shows the strong deviation of the Shannon entropy and analyze these states. So we calculate the phase space, semi-classical phase space distribution, or the Husserl distribution of these states. And these are shown in this figure. They clearly shows that there's a high density, phase space density around this pi value. So these are like the reminiscence of this unstable pi mode. Also, certain states shows the oscillation, the orbit around this pi oscillation. So these are like the clear signature of the scars in this system, in the states. Also, we can describe this type of unstable steady states by this coherent state structure, which is called as pi, which we call pi, which is just the coherent state, product coherent state. And then we choose this type of this eigenstate and take the overlap with this pi state, semi-classical pi state, semi-classically describing this pi mode fixed points. And then we find that these states which are deviated very, which has a Shannon entropy is deviated from this limit, they show a very strong overlap with semi-classical pi states. And this is a one signature of this scarring phenomena. And also we find that the degree of scarring, what I mean by the degree of scarring is that if you see this phase space density, and if you here you see the strong localized structure, but the localized structure will become faint later, but as you increase the instability of the system. So by increasing the coupling strength, then one can find this the instability of this unstable pi mode will increase, and that will show that the visibility will also decrease with that, and also the overlap factor that will decrease, so that will give the degree of scarring in this system. So okay, and another interesting point is that the states, the scarred state that violate Berry's conjecture. So typically Berry's conjecture says in the ergodic states that all the amplitude of the states, they follow a Gaussian probability distribution, or in other words, they have some sort of things called, in the random matrix context, is called the Potter-Thomas distribution. But we found out there is a strong deviation from this Potter-Thomas distribution for these scarred states. So Berry's conjecture is violated for these states carrying the scars. And also the survival probability, the dynamical signature of the scar states can be found from the survival probability. If we start with this coherent state corresponding to this pi state and see the time evolution, then we see the very short time scale, we see this type of oscillatory behavior, type of revival and oscillatory phenomena in this case. And then in the long time, it is deviating from the random matrix prediction of the survival probability. So there is some random matrix prediction of this survival probability in long time, and it shows a deviation from this. But whereas if you just consider the same energy density, some arbitrary initial states, initial coherent state, that show very rapid uh, decay of the survival probability and converges to the random matrix prediction. And another observable effect of this card state is the phase coherence. So so far we are considering the relative phase as a classical variable, but actually this is a quantum state. So this is a phase, states can be defined in this way, and one can calculate the phase fluctuation in this Josephson dynamics. So phase fluctuation, the better way to calculate is that cos phi average. And if we calculate for these pi oscillation states, when the pi state is of course unstable, but still we see that the this cos phi average, this thing that shows a phase coherent structure, whereas other state that shows a decay to zero, that phase phi, so that shows a phase diffusion phenomena. In that sense, for any ergodic or random states, it shows a phase diffusion. Moreover, after the evolution of this pi state and for any other random coherent state with the same energy density, we find the two different structure. In this case, after the time evolution, we still see there is a accumulation of density around this pi point, whereas the a random state show a very random density, phase space density. In that case, there is a clear deviation from this. And this is a very nice experimental, can be experimental signature for studying the scarred states. Okay. Okay, so this is the first part of this Bose-Josephson junction, etc. But similar phenomena can also be studied in
Hi,
the.
Subhasis, you have
Okay.
10 minutes.
Okay, so I'll just finish within. Okay. So another example is a kick-top model. In fact, this kick-top is a this described by this Hamiltonian. It has been studied in the context of quantum chaos and has been realized in the cold atom experiments like these chromium atoms. And although the spin is not very large in this case, and also this has been realized in the superconducting qubit, so where there is a one part is the sx, and there is a periodic kicking term is described by this. There's a periodically the spin is kicked with a time interval t, and the mu represents the kicking strength of this thing. So this system we have actually this model we analyzed is described in this paper with my student Devabrata Mandal and Shudip Sinha. So that was a different model. We considered basically a coupled top, a kicked coupled top model, but in some limit it turns out to be the exactly same as the kick top model. And since kick top has been observed in or realized in this cold atom experiment. That's why I'm just focusing on only this part, the scarring in the Kirchhoff model. So there also we can derive the classical equation of motion in the limit of large S limit, and this gives rise to this type of a classical map. Basically, the stroboscopic evolution can be written in terms of the classical map, where n is the nth kicking in that way. And analyzing this map again, we calculate some of the, find out some of the fixed point and steady state, and the full dynamics shows this behavior. So initially there is a very nice fixed point, a very regular trajectories, and then there is a bifurcation of the one steady state that occurs. So one steady state becomes unstable, and then it bifurcates with this, and then again different type of states are forming with increasing kicking strength. And it is very interesting, in the intermediate regime it shows a mixed phase space regime. In fact, the mixed phase space regime is a very interesting, shows interesting behavior, because that shows a local ergodic behavior in the system. So certain regime is regular and certain regime are chaotic. That's very interesting. And also the quantum scar, this is the regime where one can find out the significant effect of the quantum scars. And later, of course, with a large kicking strength, this becomes completely chaotic. So we analyze this unstable fixed points or unstable steady state, and also the unstable two cycle. So two cycle is like a smallest periodic orbit that also observed in this case. So similar way, we have seen that in the basically this is a dynamical system, unlike the first Bose-Josephson junction. Here is a time dependent problem. So we analyzed it the Fluke method, and we consider the Fluke eigenstates here. So we find out the Fluke eigenstates which carry the scars of these types of unstable fixed point from the overlap of the semi-classical description of these fixed points. And this really show the Husserl distribution, so the clear signature of this trivial fixed point, and then there's a symmetry broken, or the non-trivial fixed point, etc. All these cases. And also the survival probability, corresponding survival probability, show the oscillatory behavior in that case. And interestingly, in this case, we have also found out the scars of the unstable two cycles. That behavior is very interesting. Some figure is not there, but it shows a very interesting dynamical revival, meaning type of a revival phenomena in the two particular points. So this is has a very interesting phenomena. Also, the scarring phenomena can be detected by this using the fidelity out of time ordered correlators. So out of time ordered correlators, or OTOC, has been very recently developed to understand the chaos in a quantum system which has a some exponential in time behavior, and this exponent gives the some analog of the Lyapunov exponent. But there is certain generalization which is called the fidelity OTOC. And fidelity OTOC, the advantage is that this OTOC will reduce to the fluctuation of these operators. So if we consider the total spin as a operator, as a given operator, then the spin fluctuation will be basically proportional to the OTOC of this. And it shows a very nice oscillatory behavior. The scar state shows a very nice oscillatory behaviors, or very slow growth. The particularly the two cycles, they show a very slow growth compared to the ergodic states. And this can be used to detect the signature of this scarring. So we see that the local behavior of this ergodic behavior can be understood. This is a from this mixed phase structure. So in this side, left side, we have just shown the classical phase portrait of some model, and here is a right hand side. This is basically the entanglement entropy and survival probability. So this fingerprint of this dynamical behavior can be still observed in the entanglement entropy or the survival probability, which actually quantify the degree of ergodicity in the systems. So there is a clear dynamical route to ergodic behavior in such system, can be understood in that way. Also the quantum scarring phenomena can be understood. So this unstable, so this understanding this connection between the unstable dynamics and quantum scarring phenomena, I think the collective spin, collective models plays a very important role. And also it will be interesting to investigate the higher energy collective states of the many body systems. and OTOC or FOTOC can be used to study the dynamical signature of quantum scars. So thank you for your attention and effect.
Hi, Subhasis. Thank you for a very good presentation. Now we have time for two or three questions. So anyone? Looks like there are no questions. So I have just one sort of curiosity, Subhasis. So you were mentioning
Okay,
that
yeah, yeah.
this quantum scarce, it is sort of in the case of a single particle, there is a sort
Yeah.
of a direct comparison with the classical system. But in the case of
Mhm.
quantum many-body scale, is there some sort of a classical counterpart to that?
Yeah, that was the question, that what is the
Mhm.
classical counterpart for the many body system. So this is not very clear, but if you consider this interacting system, like of course if you consider the Josephson junction, for example, of course it is a many body and interacting system. However, since there is a collective description is possible in such system, in the large n limit, one can write down the classical equation, etc., so that the correspondence can be understood very clearly. Okay. But there is a recent work to understand this classical thing from the matrix product states. So if one start with some type of a product ansatz of this matrix, meaning not well, some type of a ansatz of the matrix product state, and try to get a corresponding equation from the variational dynamics, then it also can show type of a very interesting mixed phase space behavior that was recently observed in cases, but not every cases it is very clear, because
Yes.
the mechanism behind this many body scarring, still there is some sort of an emergent symmetry is turns out to be a basic mechanism. So there is certain state turns out to be very protected, symmetry protected state, and which does not mix with the other chaotic state, so that if you start with a mixture of those particular states, then they will just show a revival kind of phenomena rather than a decay or thermalization.
So if there are any other questions, then we can thank Subhasis for a very nice talk, giving us a very good account of the quantum scar states. Okay, thank you, Subhasis.
Okay, thank you.